Hello everyone. So, per user request, I do want to go over a little bit of maybe just looking at what the national exam looks like. Because we have high hopes here, and we will get to the national exam part. Okay, so let's say, okay, and this will only be like 1 minute. Okay, 1 second. Wait, okay, so let's say iron sulfide reacts with gaseous hydrogen chloride. Okay, doesn't matter really that it's gaseous. Typically, I don't think it will. So it produces iron 3 chloride and hydrogen sulfide. So you really just switch places. Yeah. So essentially, it just seems like you're just switching places. But that doesn't even matter anyway. Well, it kind of matters. It's good to write out the formula. You want to know what's happening in the chemical reaction. So, so yeah, so you have iron sulfide, right? I mean, what? Sulfide? S? Sulfide. It's just S. Right? Interesting. Yeah. So iron 3, so 3 just means it's donating 3 electrons. Okay. So, and you're adding it to plus hydrogen chlorides. Actually, let me just make sure iron sulfide is just FeS, and it's gonna be, yeah, FeS, but that's iron 2 sulfide. We have iron 3 sulfide, so that would be, so you have to balance because the sulfur can only take 2 electrons. So if the iron is donating 3, you need, you need it to make sense. Each iron's donating 3. Well, FeS doesn't work because one's donating 3, one's accepting 2. What's happening with the third electron? It's supposed to be accepted by sulfur, but it's not. Sulfur only accepts 2. So I just cross multiply in order to make it make sense. So 2 irons, 6 electrons donated, because each iron donates 3. 3 sulfurs, because each sulfur donates 2. Accepts 2. So that's going to be 6 accepted. So this is 6 accepted, 6 donated. It makes sense. And then hydrogen chloride. And it's going to produce FeCl, but it's probably going to be Cl3 because, again, it's iron 3, and each chlorine actually accepts 1. You should know this based on prior knowledge. And then you have hydrogen sulfide. And again, each hydrogen donates 1, so thus hydrogen sulfide would be H2S, because this will accept 2. Each of these will donate 1, so you need 2 in order to make a sensical molecule. And yeah, and you just know chlorine accepts 1, and the way you know this essentially is wait, it's already on the test. Just how far it is from here. So these will take 1, these will take 2, these will take 3. These will give 1, these will give 2, and these will give 3. And I've seen various things here. Typically, well, I feel like a larger introduction on this. If you already know this, then just skip this part of the video. So essentially, we notice that these all are very stable. Those won't react with much. These we observe are only stable, I guess, when it appears that when a certain something happens. And here, this will only be stable when 2 certain something happens. And that certain something is just based off of a bunch of experiments. They've just concluded that that somehow, like let's say you have Na, right? It's attached to sulfur. You have table salt. It's stable. But if you have Na and it's attached to O, you're going to need twice as much in order for it to be stable. So we kind of just have this table, and it's organized by mass as well, and essentially So that also is the reason why it's like organized this way. And so this is like most stable, it just stops here. And it's not just that either. So yeah, we know it's okay. So it needs, this kind of needs like one, we call it like an electron. That's what we kind of believe. It needs an electron to become stable, 2 electrons become stable, 3 electrons become stable, and every time you have the most stable stuff, you go to the next row. Also, the fact that on the next row, you're going to be at a new energy level, which essentially means, like, let's say this has 1 electron. It's going to be, near the nucleus of the proton. But let's say we have lithium. Lithium has 3 electrons, typically. We're going to say, right, that 2 of the electrons, they're going to be, near this, in the same sort of region. And this is the nucleus. Yeah, these are like kind of in the same sort of region, like for helium. So okay, actually let's draw helium. This is helium. So hydrogen is without this electron. Helium has both electrons, and yeah, they're in the same sphere. But with lithium, there's a 3rd electron. There's also more protons in the nucleus, but ignore that for now. So there's a third electron, but it's further away. And let's go, okay, maybe to sodium. Well, actually, no, not sodium. Let's go to the beryllium. There's just another electron in this orbital. And you keep going, all these, you're just gaining electrons. Although, these over here will have, like, electrons in a different space. Like, let's say, like, it's like a shape like that, right? And then there's another shape like that. But it's still always like in the sort of outer layer, the 2nd layer. When you get to sodium, it's in like a 3rd layer. So that's kind of like what we've obtained informationally based off empirical observations. So yeah, for this question, so we already know, how many each will donate, how many each will receive in order to be stable. Because again, it's only stable when it's kind of at this sort of character where it has somehow, we feel it's obtained electrons, this sort of entity that allows it, when it's at a certain amount, like these, they'll be just as stable as these. So, over here, chlorine needs to take 1, so for every Fe that it'll be ionically bound to, you'll have 3 chlorines. Because Fe is donating 3, each of these will take 1 in order for it to be stable. It's going to have like this sort of formula. H2S, H's are going to donate 1, sulfur is going to receive 1. But then you need 2 H's, and then, these are I don't know if I'll say these are ionically bound, but don't worry about that. Hydrogen's a little different, I guess, but no matter. These general principles will apply here, and we need to make sure also, like, these aren't changing. Again, we're only dealing with electrons changing here. Protons are always staying the same. And the protons and neutrons, that's what determines, well, protons are what determine the element. So we know none of that's changing, so we should have the same amount of Fe at the end. But we don't. We have half as much here. So we gotta fix that. So we can say 2 are generated. Oh, but now we have 6 Cl's here. We only began with 1, so we're gonna, okay, maybe there's 6 Cl's. Oh, but 6 H's now, and 2, so we're gonna say there's 3. And that actually worked itself out. So there's 3 S's, so it's completely balanced. And then all we have to do now is say, we need to be like, okay, we have 1.5 moles of HCl. How much iron sulfide, so how much of this would have to react with it? Well, I don't need to do much calculation, because we know for every molecule of HCl, for every 6 molecules of HCl, we have 1 molecule of this. So, typically what students know is you're either going to multiply by 6 or divide by 6. Like, I already know, like, without doing critical thinking even, I know that we're going to divide by 6. Because for every 1 iron sulfide, you're going to make 6, you need 6 hydrogen chlorides. So thus, you're going to need less of this to make this. To mate with this. Same here. You have 1.5 moles of HCl, so you need like a 1/6 of that. You're going to need less of that. And all these answer choices are smaller anyways. So, I just divide that by 6, and what's that? Like, 0.25. And A is the answer, A, and this is the national exam. The answer is indeed A, and we have solved this problem easy peasy. Peace.